Let me introduce myself first. I'm Kolesa. I work for the Samsung open source group in the UK, in London. I've been with the Enlightenment project for about since 2008, and in 2014 I joined Samsung to work on the Enlightenment Foundation libraries professionally. So let's begin. I'm going to be talking about high-level application scripting with Lua and LuaJIT. Actually, we have this runtime which allows you to use LuaJIT and EFL to write applications. It's currently not complete, but it's getting there. It's made quite a lot of progress. So let's see. First, what is the EFL? Some people here might not know. It's not such widely known project. So let me introduce the EFL first. It's a suite of libraries for graphics and other things. We have, for instance, the actual Canvas library, GUI toolkit, networking library. Basically, you could compare it to, say, Qt, but it's actually written in C, and it's way more lightweight. It's was originally written for the Enlightenment window manager, which has been around for quite some time on Linux and other Unix-like operating systems. Originally, it was just a window manager for X11. It's no longer just a window manager. It's a desktop shell of a sort. Basically, it still behaves like a window manager, but it integrates desktop environment functionality into itself using module system. Anyways, it's scalable to both desktop and embedded systems, which is very unlike most other desktops. You can customize Enlightenment using a system of modules, which can completely change how the desktop looks and behaves. It's lightweight, as I said before. It's written in C. Has C APIs. It can scale to mostly anything which has at least 32 megs of RAM for the entire system. So it was used in some very constrained devices previously. It doesn't even require X11 or anything to actually run. It's the significant usage includes the Tizen platform by Samsung, which is used in quite a few products by now, such as smart TVs or watches. So there are 2 phones now which are sold in Asia. Anyways, what are the components of the EFL? Historically, it's been a few separate projects, each with their own build system. It's no longer the case. It was mostly merged together in version 1.8. It's still separate libraries, but the build system is shared. This was because many people have been complaining before that it's very tedious to actually build the EFL, because you had to first build some of the libraries in correct order. People were making scripts to actually get things built more easily and stuff. So we decided to merge. EFL is the core library set, which is built and installed at once. It includes the core stuff like C utilities, the scene graph canvas, and other things. Then there's Elementary, which is Widget Toolkit built on the core EFL, which is still not merged into EFL itself, but it eventually will be. There are some others which are still independent, such as EVAS generic loaders, which is like image loaders for vector graphics and kind of stuff. Anyways, what's EVAS? EVAS is the oldest EFL component. It's a scene graph canvas created way before other toolkits had similar functionalities, such as Qt with QML and stuff. It represents the canvas you have as a state of objects. EVAS objects, these represent, for example, primitives such as rectangles or images or text or actual widgets in the scene. It itself provides some of these primitives which can be used by other libraries to build further, more complicated things. Obviously, widgets provided by Elementary, for example, or there's the library called Emotion, which provides a smart object for video, which can be used as an ABS object. The idea is that you can combine different types of Avast objects provided by different libraries within a single application, and it'll actually work seamlessly. And there's eCore, which provides the interface between the OS and the rest of the EFL, which means, for example, when running Enlightenment applications on X11, eCore provides the windowing state for X11 and input handling and that kind of stuff, while Avast itself is just a canvas. It has interaction with different types of systems, including X11 on most Unixes, Wayland on Linux these days. We have actual complete Wayland support. Actually, we had it before most others did. Enlightenment itself now also has complete Wayland support as its own standalone compositor. It doesn't depend on Weston or anything like this. Well, for example, GNOME uses Weston instead of actually providing its own compositor. We support SDL for when it's supported, Cocoa on Mac OS X, DirectX on Windows, or GDI on Windows, or several other backends. So we can even run in plain frame buffer or directly on top of DRM on Linux and POSIX systems, which actually ported the graphics stack. So it's very portable. Once you write your application, you can run it in different places very easily. And it also provides a main loop for applications to use. Basically, if you want to use the EFL, you need to use eCore to provide the main loop. You could potentially write your own main loop if you wanted to, but and obviously use Avast as a standalone thing, but that's something most people wouldn't do. It's complicated, and several other things unrelated. Edge is our layout and UI description language. Basically a declarative language using which you can describe layouts of UIs plus some primitives plus programs, which you can use to describe stuff like transitions between two states and the animation they will use. It also allows some basic embedded scripting in our own language, which is based on the small language, if you ever heard of it. And there's also basic very sandboxed scripting with Lua, but this is not completely related to this talk. It is also a way to compile set language, the declarative descriptions, together with, say, pictures, fonts, and other media, together into a single file, which you can load through the C API. And that way you can basically decouple the application itself and the UI of it. Like you could then provide custom edge files, which provide a completely different UI. As long as the signals are preserved, you should be fine, and you can replace it completely. Widgets provided by libraries such as Elementary or the video widget provided by the Emotion library can be embedded in Edge using special elements called swallows. Basically, you can declare these in your Edge layout and then inject widgets from C, like any Avast object, doesn't have to be a widget, into these elements, and that way combine Edge style layouting and classic style widgets. Now, Elementary. So Widget Toolkit, kind of similar to, say, GTK or Qt or the others. It provides widgets written with Avast. It can be used standalone, like GTK style, where you basically avoid using Edge completely, and what you do instead is declare a layout from inside of C or the favorite language you use. Basically just a classic style hard-coded layout inside of the application. Or you can combine it with Edge, as I said before, and get more flexible layouts. It all depends on the application you write. Now, EO, it's very related to the last stuff I'm going to be talking about, because it's the object system for the EFL we introduced a few releases back. It's the base for all EFL 2.0 APIs, which will be coming we are not sure when yet because it's still heavily work in progress, but it'll be done eventually. And it allows for backwards compatible legacy APIs, which are important because we need to preserve compatibility with all the old EFL APIs. We're going to provide sort of legacy wrappers around the new APIs to preserve everything. It provides everything you would expect from an object system. It has some sort of inheritance. It provides interfaces, other, like obviously virtual methods and other things you would expect. Much of the EFL 2.0 APIs is actually interfaces, which you can implement on your own stuff, and it's all done in C. And what we aim for and how we differ from different such systems is that we aim for both API and ABI stability. So you can introduce new methods into your EO classes without actually breaking anything, which is very unlike some other systems do. Anyways, overview. What is this talk actually about? We're kind of tired of writing everything in C because it's very inconvenient. Not everyone likes to write applications in C, especially mobile developers or people targeting embedded devices, such as devices without a memory management unit, for example, would be very tedious to actually deal with everything. So there has to be some better way, and obviously the idea was scripting languages. We had to pick a scripting language. They all kind of suck in some way or another. So, which one are we gonna pick? Why is that? Why are they bad? They're obviously slow compared to native programming. It's a main concern usually. There's a lack of proper type system. You usually cannot avoid this. And there's a lot of bloat we don't need, such as in Python you have the huge standard library, which is nice for some things, like when you need to quickly create things, but in some cases, like ours, it's completely counterproductive. We don't really need all the batteries included within Python or some other languages. Binding them is very inconvenient. If you ever dealt with for example, the API of CPython or, say, the V8 engine for JavaScript, the APIs are all quite ugly and it's very difficult to deal with. And obviously another thing is they tend to be very resource heavy. And on mobile devices, battery life is a big concern. We want to minimize power usage. This is sometimes not possible with scripting. It's just too heavy for that. Maybe if there's some solution. Anyways, I'm going to go through a few scripting languages and compare them and how do they measure up. First, Python. It's a language many people know and people like it, but it seems there's a lot of issues. It's slow, like the Python interpreter is among those slower ones. It's also big, bloated. It doesn't work on the devices we target. It cannot work on the devices we target. There's no decent unified API for embedding Python inside applications. So what you get instead is like for convenience wrappers such as Boost Python and C++, which is something we didn't really want to deal with. We have the C library and we wanted something which is very easy to embed. And there are some language design issues such as lack of proper lexical scoping, other things. Ruby, it's not that obvious choice, but it kind of is, I guess. There's problems again. It's again slow, it's again bloated. There's no API like decent one again, and it's also difficult to embed. So mostly the same set of issues as we get with Python. And there are some language design issues as well, like, pretty much the same stuff. Perl. Now, it has a lot of problems again. It's again slow, it's again bloated, and there's no API again. Okay, have you noticed the pattern among all these? So, JavaScript is another potential option, and it's very popular these days, and many people use JavaScript. There are several engines. Some of them are very fast, such as the V8 engine from Google, used in Chromium, or the SpiderMonkey engine from Mozilla, which also has a decent JIT engine. But all of these have completely different APIs, and these APIs aren't particularly nice to work with. I tried, and the language, obviously good thing is there's decent JIT implementations, very fast ones, because the web browsers keep going forward, and basically they need performance in order to make up for the slowness of bad scripts on websites. These days it's very much a necessity. As I said, each implementation has its own API, which is kind of inconvenient, because if we wanted to embed JavaScript, you would have to either target a single runtime, or we would have to write different modules for different JavaScript engines. And the language is pretty bad. For example, if you've seen the comparison table of JavaScript equality operator, how different types of values compare and how they convert, it's a huge mess. So it's still probably a better choice than the previously mentioned ones for this particular thing, because it can be embedded fairly easily. But still, there's a few others, like IO, Self, Scroll, and the others. And there's a lot of choices, but most of these are interpreters, fairly slow, mostly slower than, say, the Lua interpreter. And some are decent languages. I wouldn't have anything against using them. I can learn new stuff, and most are fairly light on resources. But it's not good enough, and most people kind of look at us weird because they don't know these languages, and it's unknown, and they would ask questions like, why did you select this particular language? So, Lua. It's a popular scripting language used in many different applications, so people know it. It's a good language. There are no significant design issues. It's mostly well designed, with a few minor quirks which are present mostly any language in the world, so nothing we can avoid. It's light on resources. The overhead is really low, and it has great embedding API, which is much better than everything else we can get. But it's interpreted, so it's not particularly fast, and on some devices it might be a problem. So we get LuaJIT. Why is LuaJIT awesome? It's one of the fastest JIT compilers you can get today. It even in some cases has performance which comes close to plain C, and at the same time, even though it's so fast, it has a really low overhead. This API is exactly the same as Lua's API, which is great, because you can use LuaJIT if you are familiar with the Lua C API, and it'll still work. The API is even compatible with Lua 5.1. So you can just use LuaJIT in a drop-in way. When you have Lua 5.1c modules, compiled ones, you can just use them with LuaJIT without any trouble. The bytecode is portable, which is fairly important for us if we want to ship pre-compiled bytecode of some applications. It might be important because for different devices, different architectures, say mobile applications for ARM, or desktop applications for x86, we want bytecode which is portable and can be reused on those platforms. This is not the case with standard Rio Lua. It's the bytecode you get is different depending on which architecture you run it on. So I guess we have a winner, and there's also a few reasons why LuaJIT kind of sucks. The VM is written in assembly, so it's not portable to architectures it doesn't explicitly support, which might be kind of an issue, but these days it has fairly decent support for different architectures. So we have x86 obviously, we have x64, most common, we have ARM, there's work in progress support for 64-bit ARM, there's Mapes, obviously. There's upcoming support for Map 64, PPC, PPC 64. That's basically everything we need to cover. There's nothing which is missing, at least for our use case. So it's good enough. And the other reason, the other bad thing is the classic LuaC API is not JITed. When you call functions which use the LuaC API, then it aborts the trace and you get some slowdowns. It's usually good enough even then. A handful of other things are not JITed, such as the bytecode to create a closure is not JITed. So it's kind of inconvenient, and much of the standard library is not JITed, especially in string processing. But still, it's really fast and really nice in most cases. And multi-threading is also an issue. It's an issue with pretty much any scripting language. There's usually either a global lock, like in Python or Ruby, or there's just nothing and no sort of thread safety at all, which is the case with Lua and LuaJIT. So what we would have to do is create a separate state for each thread, sync them somehow. So that's kind of an annoyance. And LuaJIT 2.1 significantly improves the entire situation. So more bytecode is JITed, more standard library is JITed. So it's faster, there's a lot of speed ups in many areas. Now, eLua. What is it? It's an application runtime we created for the FL a while ago. It's basically kind of small loader, which is partially written in C and partially written in Lua. It ships with EFL itself. So if you write EFL applications with Lua, it's basically guaranteed you will have the functionality. If EFL is installed, you have Lua. It's lightweight, and it's very small, and it's reusable. Most of it is written in Lua itself, so you could possibly have different loaders for custom applications. What is it supposed to achieve? We want to achieve rapid application development on different devices. For example, desktop applications and mobile applications on Tizen could be eventually written in Lua, which could be nice. The code is supposed to be clean and high level, and it's also supposed to be lightweight and have good performance. So this is what LuaJIT helps us do. We also aim to get easy distribution through the App Store model, and obviously more safety, which is one of the main benefits of using a scripting language, because you don't get segfaults and these kind of things. It's safer. So how does it work? It's split between a binary, which is very small, and a library, which provides much of the functionality. And the library provides utilities to actually initialize the ELA state and help it set up, like figure out the path to where Lua applications are stored. The binary is a minimal launcher which uses the library for itself. Together they set up the state plus main loop from eCore, which is, depending on the application type, it will either start or not. Depending on if you just have an application which is like one-off run, which ends right after you execute it, or if it's an application which actually continuously runs, such as pretty much all GUI applications. Most of it is written in Lua itself, so there's very little C involved. C has stuff like, say, bytecode caching, which we implement, where similarly to, say, Python, if you run a Lua script, it will compile, save the bytecode, cache it on the disk, then load it as needed. Bindings. Bindings is obviously a huge issue with scripting languages. Many bindings in Lua suffer from a big problem where they get out of date because people forget to update them, and it's also hard to keep up with some upstream projects which keep introducing new APIs. So we need to deal with this somehow. A decent application runtime needs those APIs, and writing them is a huge pain. and maintaining them is a bigger pain. So what do we want to do? Aeolian. What is Aeolian? It's basically two things, and it's an API description language we invented. You can use it, or it is used to actually describe most APIs present in the EFL. It's also a library to parse this language and turn it into sort of a database in C, which you can access and actually use this information. Well, not all, but most APIs are now described with it. We can reuse this information gained from these descriptions to actually generate bindings. The language is designed to actually be mostly independent of this. There's no maintenance burden because bindings are generated by the time you build the EFL. There's no such thing as manually writing bindings. Now, LuaLin is the binding generator for Lua. It uses the Aeolian library. We have it by itself is written in Lua, and it's an application which runs using a runtime. So it's also sort of a test for this runtime. It's easy to maintain. It's high level because it's written in Lua, obviously, and as I said, bindings are generated by the time you build the EFL, so you always have them, they're always up to date. How do these bindings work? LuaJIT provides an FFI interface, which can be used to interact with C directly without actually having a compiled C module. So this allows us to directly access our APIs as they are, and our generator generates bindings powered by LuaJIT FFI. For different languages, we have several different generators by now. One for C++, people are working on generators for Rust and OCaml. So we're also JavaScript. So we're gonna have different languages eventually, but Lua is basically, along with C, the main one. So how does EO and Lua interact? We have sort of Lua EO layer. What basically happens is the core EO API is not generated, it's manually written, and it declares the required functions through the FFI, then creates an FFI structure meta type, which implements several meta methods, which are used to provide sort of native feeling, general way to actually call methods and these kind of things. So this provides the core, and it handles, for example, signals for callbacks, method resolution. The generated bindings are very small, very simple, basically just declarations plus a bunch of wrappers. Basically, most of the functionality is done by the EO core scripts instead of actually generating the code for them, which means the amount of generated code can be greatly reduced to basically bare minimum. I can show you how some of the generated bindings look afterwards. So we get APIs which feel native in Lua. They are still automatically generated and they're pretty much usable. There are a few other APIs provided by eLua. Like a collection of Lua utilities which are useful for like application development. And this provides a Lua side object system, so eventually you'll be able to, say, inherit from EO classes inside of Lua and provide your own extension functionality on your own. Bindings to most relevant components of the ENA library, which is a collection of C utilities such as containers like lists, hash tables, arrays. We need to interface these somehow because our APIs in the FL deal with these, and we need to somehow convert them to a Lua side representation, which actually feels right. In Lua, it must be a table, obviously. So what we need to do is convert this efficiently. Sometimes we do not convert. Sometimes they provide like objects which you can read from, and you have to convert explicitly. This is because if we converted all API results to actually have big Lua values, there would be lots of copying involved, which would result in performance decrease. So you can use this object directly for reading. So for most things it's okay, and for when you need to do something else with it, you just copy it explicitly. These are used by bindings, obviously. And EO interacts with the Lua side object system we have. And it's all completely transparent. There's nothing which would feel non-native. So how do we do distribution? Because it's bundled with EFL, it's always available, as I said. And we're gonna have sort of EFL App Store thingy to promote development and distribution of EFL applications. So you'll be able to upload these EFL applications here. It'll be kind of similar to, say, in Lua there's LuaRocks. In EFL we need something to distribute EFL applications before they get to, say, Linux distributions, BSD systems, or other means of distributions. Basically get them to users before they're available somewhere else. It must be well supported. We have to encourage people to write apps, which is what we are aiming to do. And it must closely match EFL APIs. This way we also get documentation for free, because EFL APIs are already documented. They're documented within the API description files. So the generators can also generate different styles of documentation for different languages. For example, like for C it generates Doxygen, for Lua it can generate something else, for Python it can generate something else, basically whatever we need. We need a self-contained package format, which we're gonna introduce. EET is our binary encoder thingy, which is used to, for example, encode Edge files. So we could use it here too. We want to make it possible to run Lua apps on Tizen, so people can eventually use Lua to actually write Tizen apps, mobile stuff. So, what's the status? We have a solid base which kind of works by now. After a few months of work, the binding generator needs some work, such as like we need to generate documentation in some format, which we are not yet sure what format. There are not too many good binding generators documentation generators for Lua. The library needs a lot of work, and the EFL interfaces need work, because they are currently incomplete, which means in those API declaration files, certain types like structures, enums, are missing. We have support for them in the library itself and in the description language, but they are missing from the description files themselves, which means we cannot currently generate fully featured bindings just because of that, because it will result in some declarations being missing. So we need to fill these in first. EFL Interfaces is a length project, and it's meant to design and implement EFL 2.0 APIs. It's based on EO, obviously, unlike the previous API, which wasn't. And this is generated to bindings because, as I said, it is not complete, missing definitions. If we complete them, we can validate them. We can activate a code subroutine, which is already written, which will do complete type verification on those EO files and catch any sort of error before the bindings are actually generated, which will save us a lot of effort, because they will just we'll know about any sort of error before it's actually out. It will guarantee definitions of types. If type is undefined and you try to use it, it's automatically an error. Obviously the bindings will be much better quality afterwards. So this means it's not fully functional, and many will fail to load completely because of the missing stuff. And dependencies are currently not handled completely correctly. And elementary is currently not handled at all. EFL itself is, so it can be used a bit. What we have, like test code, it works with what we have plus some manual adjustments which have to be done, so it's not fully functional. Some other issues are, like for example, internationalization and localization, because if you use GNU get text, you need those MO files which are loaded by the library stored in a physical location, which is not good for us, because if we want to package those applications, we need to store it in some sort of VFS and read it later. So we need to figure out some custom way to deal with this. We need seamless VFS for those packaged applications with the same APIs, standard Lua IO streams. So if you try to open a file with a VFS location using IO open, it has to work. It has to feel just like normal Lua. We need to figure out sandboxing, which is also kind of difficult, and we need to minimize the startup time we have, because for mobile purposes and slow hardware, it needs to be as lightweight as possible. And we need a portable bytecode loader. So, how does it work? Everything starts in the launcher, and the Lua state gets initialized as usual, just a standard C Lua state. Lua itself supports sort of application lookup path, which is sort of similar to package.path in standard Lua, but it's used to load Lua applications. Applications then get executed, and the main loop is started depending on if you return from the application or not. In some cases you might want to return because it's just a command line application which ends right away, there's no GUI. This is the case, for example, with the generator for the bindings we have, because it's just a generator you execute it in command line and it doesn't go anywhere else. Lua provides a custom module system which works outside of Lua, and it's seamless. It replaces require for us, and our module supports sort of init shutdown callbacks if needed. So we can hook, for example, library loads, unloads using FFI to these callbacks and actually safely handle things. They take care of opening those libs. Library system. The C libraries are opened and initialized as necessary. They're sort of cached because we need to have control over how things are loaded. And EOLIN generated bindings actually generate those callbacks correctly, so things are handled right. The symbols, the API functions are retrieved as standard stuff using C FFI. And this is wrapped in sort of high-level API. There's no FFI exposed to applications themselves, because obviously FFI is unsafe and it can result in seg faults and other types of issues. You shouldn't have to be able to access such low-level stuff in applications, so we don't. I already talked about this, so they provide simple Lua APIs. They feel like Lua objects, basically. So if you have the C list or C hash table or anything, it provides sort of meta table based interface to actually feel right. We have many of these, like accessory, iterator, list, log file, and others. It will be expanded as we need, if we need to. In other modules, we have a benchmarking module which we can use to run tests. Command line application, command line argument parser, which is also standalone, and I put it on my GitHub. The Lua generator is included, and the custom module system, and the OTL module, which provides the object system, library system, string buffers, and some other stuff which is useful and used. Conclusion: it's still largely incomplete. We need to work on this more, but it's getting there. It's much better than it used to be already. Those AO files need work because we need to fill in all those types to actually make things generate 100%. And the validator, which is already written, needs to be enabled. But before we can enable it, we basically have to complete the other stuff. The Lua APIs need plenty of work. Obviously, EFL APIs themselves need work because the current APIs do stuff like use function pointers in many places where they wouldn't have to be used, which creates an issue for Lua because it's hard to interact with callbacks via FFI. There's some complications like the limit on callback count, and doing it through C library is something we would like to avoid. So we have an event system in EO which can be used to replace most of these function pointers. So you can just replace this using events, which is already implemented by the runtime, and it'll just work. Anyways, thank you, and now I'll show you some of the code, maybe. The resolution is somewhat inconvenient. How much time do we have?
20 minutes or so.
Okay.
Enough?
Yeah, sure. For example, this is slow. When something froze. So this is basically how the file looks. There's we have two types of files, EO and EOT files. EOT files are basically files which provide types like structures enums without a class definition. So we can import these to share some types between different EO classes. This syntax is quite familiar. There's just a class declaration plus some inheritance. You can provide some additional annotations which are used for C generation mainly. And then you have categories like methods, which describes properties and actual methods. Properties are annotated with sort of tag name. Set get, basically what happens when you try to set a property, when you try to retrieve the property. And properties obviously also have values, which is the value which gets updated. There can be several values which gets updated. Now an example of actual regular method. We have mostly properties here. For example, there's a name plus a list of additional tags plus documentation, which is included structurally in this way. Return tag, for example, defines which type is returned from the method. Arguments, whether they are in and out, or names and types. We use different type syntax from C, sort of more function-like to make more sense than C with const and pointers. So it should be easier to understand for most people. Obviously, out arguments will automatically add pointer as needed in C. So you get, you see some of our EO files are quite large. Now, from this, Lua file is generated. This is automatically created, so it includes basically the main modules we need, plus some things you further pass to the loader. We declare some variables which are required. The init callback is here. There's no end callback in this case. So we basically retrieve the EO class from the declarations and then register the class within the wrapper interface we have on Lua side, which is written in Lua. So it's registered. There are some parameters for it, plus the body, plus the EO class, which is a C handle. Then it obviously generates FFI declarations, and then it creates the body, which is basically, you can see it's very simple. It only, here it's constructor, here it's like methods. You see, for properties it generates both methods and actual property syntax. So you have like very simple wrappers in Lua. And then at the end, properties and events are marked using this kind of declarative syntax. So, for example, in properties, these numbers mostly define how many values are modified, how many values are like extra arguments, how many values are returned and stuff. So basically just definitions. There's no actual code involved in this. It's just the simple generated stuff. And then it generates sort of a global or module level constructor which calls the FFI functions to retrieve and instantiate the class itself using all the extra arguments. Now, this is all backed by EOLua. So this is the EO bindings. You have like, these are manually written. So for example, here we have event system handling for signals. It's sort of, there's a one base class, EO base, which everything inherits from, like in some other languages. It provides like empty definitions for properties, events, and everything. Now there's, for example, constructor calling, and this is how basically the method resolution works. The meta table is assigned to the handler you get from C using FFI meta type functionality. This is basically the meta type. There's index, which will first retrieve the number of keys from the generated registered structures, checks and does some sort of error handling, then checks the numbers and properly executes the right paths. So new index is used to assign and is also used to retrieve for when there's multiple returns. There's one path which is really slow, and I try to optimize it, but fortunately it's very rarely used, so it will not affect performance in a meaningful way. In any case, the implication of this is basically when you have any objects, you could do something like this. Like instantiate button, and then if you want to say set it's you could do both this, or you could do both like this. Anyways, yeah. The ELO loader supports some basic options. You see, this is how I invoke an application. This is the generator for Lua bindings. The applications can have their own command line paths. You basically pass the application name to the loader and then pass any further options. This is the help listing for the generator itself. So you can give it, say, an EO file. And there's error parsing because it's not found. Anyways, this is how you would basically invoke it. The generator itself is also very simple. Broken. Basically, very simple bindings using FFI. And then, because we have those bindings and we have a very simple API for EOLIN itself, we can just write the entire generator in Lua and don't have to deal with stuff like string processing in C or similar things. You have some type mappings. Basically, just pure Lua code, idiomatic stuff. Anyways, this is about it. Are there any questions?
Yes, one question about the big picture of all this. Is the goal to write the entire user interface of applications in Lua for Tizen or?
Sorry, could you repeat the question? I didn't hear.
What is the goal of this library? Is it to write for the application developers entire application in Lua?
Yes, you'll be able to write basically entire EFL applications in pure Lua. That's basically the goal, because currently all EFL applications are written in C, and the applications developers obviously mostly don't know C, and if they write C they will make mistakes in stuff like say memory management. They have to manually allocate their things, and it's inconvenient to work with. So we want to provide Lua as a scripting language for applications, so application developers can write safe applications easily for different platforms, including desktop, Tizen, and other environments.
Which desktop platform do you support currently?
Sorry, what?
Which desktop OSs do you support?
Well, basically all OSs which EFL is supported on are supported. So it's basically Linux, BSDs, Solaris, I guess Mac OS X, Windows, possibly other Unix-like systems. Mostly everything that is relevant, really.
Windows, because I couldn't find it. I tried to find if there was a library for that Windows.
There's builds for Windows if you're looking for that. There's I can show you. I think the cloud has terminated, so I'll just there's this site which does packaging of different software for Windows, including EFL. They actually have a package manager which is written with EFL itself in OCaml. So this is basically written using the elementary toolkit, and there's EFL in it. You can install it easily from there.
You have to install it from if you want to distribute a Windows application.
What you can do is either provide EFL with the application, obviously. You could do this either by providing DLL files or by statically linking your application against the EFL. It shouldn't be a problem license-wise, because EFL is mostly BSD licensed, so that should be good. Or you can just make people install EFL, but that's not convenient for most Windows users. So what you will want to do is ship EFL shared libraries, I guess, with the project, and that's the most convenient way, I would say. It's fairly small, I would say. For EFL distribution, you would need for script with debug symbols and stuff. It could fit within a few megs, maybe space. Plus, you could obviously have also more minimal build, providing only the functionality you require, which could cut down the size even more if required.
More questions? All right.
Thank you.